EDX Corpio, vectors 2, equations of lines. The vector equation of a line in 3 dimensions. The vector equation in 3D has the same form as a line would in 2 dimensions. R equals A plus lambda D. R is our general point moving along the line. A is a known position vector of a point on the line. Lambda is our parametric value, which allows us to move along the line. And D is the direction vector, or a direction vector for the line. So for example here, 2, 4, 3. 2, 4, 3 is a given position vector of a point on the line, and 1, 0, minus 4 is a vector which is parallel to our line, and lambda is the required scalar multiple to allow you to move to different positions along the line. This vector r is not some strange new quantity. All it is it's the position of a general point on your line. In other words, it can be considered as being x, y, z, and in later lessons we will use x, y, z as this general position vector. We can now see what this means on this GeoGebra file. So here we have a given position vector, minus 1, 1, 2 on the line, and we've told the direction of this line is 3, 1, 1, and we have the parametric value of lambda equals 1 at the moment. So you can see our given position vector A on the diagram, and we can move to different points B. So when lambda's 1 we are at B, and when I make lambda bigger, you can see that our general point P moves along the line. So that is, lambda is 1.6, and when lambda is less than 1, we are between A and B, and when lambda is 0, we are at A, and when lambda is negative, we can go backwards. So lambda controls the position of your general point x, y, z as it goes along the line. So in this problem we want to show that the point 5, 4, minus 9 lies on the given vector line. So the first thing I would do would be to write this vector line again using column vectors. So that's 2 in the I direction, 4 in the J direction, 3 in the K direction. Nice clear parameter lambda, and then 1 in the I direction, nothing in the J direction, minus 4 in the K direction. And we can now take it a step further and introduce our x, y, z notation. X, y, z equals, and you can even write the right hand side as a single column vector, so that's 2 plus 1 lambda, 4 plus no lambda, and 3 minus 4 lambda. We can see straight away that y is 4, so that coordinate is fine. What we need to do now is to test the x coordinate. So if x is 2 plus lambda and x needs to have a value of 5, then lambda would be 3. So when lambda is 3, we get the correct x coordinate. We already have the correct y coordinate, but it's essential when you're dealing with 3-dimensional vectors, you always check all 3 components. So we need to check the z component as well. Z equals 3 minus 4 lambda. Now we could replace lambda with 3 to see if we get the correct component, or we could replace z with the minus 9 and see if we get the same parametric value for lambda. So 4 lambda is 12 and lambda is 3. So we've got the same parametric value, and therefore the point 5, 4, minus 9 does lie on the given vector line. So when you're dealing with three-dimensional vectors, it's sometimes a good idea to do a simple sketch to get the idea of what's happening. And your simple sketch can just be draw a line with an origin, and the things we're looking for are, do we know the given position vector of a point on the line, sometimes called little a? Do we know the direction of this line? So here the parallel direction vector is called d. And are we aware that a general point P on the line has the position vector little r, which is equivalent to x, y, z. So just an awareness of what the terms are in the vector equation is very helpful. So here we have a three-dimensional situation where we've got a given point A and a given point B, and we want to find the vector equation of a line through A and B. So we're going to work out the vector A towards B, so that will be in this case our direction vector, although B towards A would have worked just as well. So we're going from A towards B, so that's the position of B. Take away the position of A. So our direction vector is going to be minus 6, minus 2, minus 2. We're going to pick a point on the line, and if I was going, as I am here, from A towards B, I think I'd choose A as my position vector. So my general point R is the position of A, so we're looking for OA, so that's 2, 4, 3, and now I'm at A, I would do scalar multiples of the vector from A towards B. Minus 6, minus 2, minus 2. At this point, if I was doing a longer question, I might decide to simplify that direction. So a perfectly good alternative would be R equals, I need to keep the same position A, don't want to be changing those values, but I could decide, instead of having minus 6, minus 2, minus 2, I could have 3, 1, 1. I could look for another parallel direction vector. The angle between two lines is the same as the angle between the two direction vectors, and that is the case in 2 dimensions or 3 dimensions. So for example here, if we were looking for the acute angle between the lines L1 and L2, if we just do a quick sketch, there's the line L1, and its direction vector is 1, 0, 4 in this case. There's the direction vector. And if we look at the line L2, so there's a line L2, and its direction vector is 1, 2, 1, we can see that the angle between the lines is the same as the angle between the direction vectors. So it's the direction vectors you need to look for when you're finding the angle between the two lines. So we need to look at that direction vector and that direction vector. In the next session we're going to be looking at the equation of a line in 3D using Cartesian form.